Hi everyone, welcome to this new lecture of hydraulic machines. In this lecture, we will solve a problem on minimum speed of centrifugal pump. In our last lecture, we have derived an equation for minimum speed of a centrifugal pump. So based on that concept, we will solve this problem. So here I have taken a question of a centrifugal pump with 1.2 meter diameter. So diameter is given and which runs at a speed of 200 rpm and discharges 1800 liter per second. The average lift being 6 meter. The angle which the vane makes at the exist with the tangent of the impeller is 26 degree and the radial velocity of the flow is 2.5 meter per second. The inner diameter of the impeller is given 0.6 meter. Determine the manometric efficiency and the minimum speed to start pumping against a head of 6 meter. So this is the question given, and here we need to find out the manometric efficiency and we need to find out the minimum speed to start the pump, okay, where the head is 6 meter. So these are the data are given and we need to find out these two things. So first of all, I'll write the data given here. Data given, we can write here, and meanwhile we need to also understand the velocity triangle for the pump. So this is the velocity triangle of the pump. So let me write some data, then we'll also discuss about the velocity triangle. A centrifugal pump of diameter is given, that is outer diameter, because inner diameter is given here. So that is outer diameter, nothing but D2. So D2 is given 1.2 meter and D1 is given here. So let me write in the near to this one. I can write this is D1. This is 0.6 meter. Again, this centrifugal pump runs at 200 rpm. So speed is given. That is speed N is given 200 rpm. And the discharge of this much of water. So that means Q is given here 1880. This is liter per second, and this one we also can convert into meter cube per second. So if you divide this is 1000, we'll get meter cube per second. So we'll get 1.88 meter cube per second. This much amount of water is discharging from the pump. The average lift being 6 meter. So the average lift is nothing but that is manometric head. How much distance it was lifted? So that is manometric head, which is given 6 meter. And the same thing also given in this here also, the pump against the head of 6 meter. The angle which the vanes make it exist with the tangent to the impeller. Now it will come to this diagram here. So this is the velocity triangle at the inlet condition. Okay, so this is inlet triangle, inlet velocity triangle. And here you see this is outlet velocity triangle. At the inlet, very simple, it is like the water is striking into this vane. This is the vane, okay, or the blade. So the water is striking to this perpendicular to this one with the absolute velocity v1, and this is the tangential velocity, or if you draw the tangent to this one, like this is the tangent is there. So the same thing, tangential velocity u1, which makes an angle of theta to the relative velocity vr1, okay. And at the exist of this, that means outlet of the vane, the absolute velocity will be come out like this, and the relative velocity which is here, that means which came here, because it is moving in this direction. While moving in this direction, this relative velocity that is going to come out here, this one, this is vr2. And our absolute velocity will come in this way, and the velocity triangle will be like this, and this is the flow velocity. Here at the inlet condition, v1 equal to vf1, but at the outlet condition, v2 is different and vf2 is different. So, and this is our tangential velocity as it is given. If you see the angle which the vane makes at the exist with the tangent of the impeller. So this is the impeller blade. So if you see the tangent here, if you draw the tangent here, this is nothing but u2. So this tangent which is given here, that makes an angle of, this is phi, to who? With the impeller, exist, this one vr2. and this one. So that is given phi. So here phi is given 26 degree. This is phi is given 26 degree, and the radial flow velocity at the exit, that is here VF2. So VF2 is given 2.5 meter per second, and diameter already have written. Manometric efficiency you need to calculate, and this one against a head of 6 meter, that is HM. So here what we need to calculate, let me write down this calculation terminology also. So calculation. So in the calculation, first things we need to calculate the manometric efficiency. So if you remember the manometric efficiency, we know the formula, we have derived previous lectures, that is GHM divided by VW2 into U2. And the second one is nothing but, that is B. B is the minimum speed required, or minimum speed to start the pump. If you remember in the last lecture, we have derived this equation, N equal to, you got some equation like 120 into efficiency, and so many like other terms also there. Let me write this, like 120 into efficiency, this is manometric efficiency actually, and this will multiply again along with this VW2 into D2 with respect to, this will be pi into this is D2 square minus D1 square. This is the formula for this minimum speed square. Even another one method is there to calculate this also. That also I'll tell you how to do if this formula is not able to remember, or if you are not able to identify suddenly in the exam. So another method also I'll tell you. So this is the two things we need to calculate. The first one, let me write the first one, that is efficiency. Now if you see this formula of efficiency, manometric efficiency, in this terminology we have all this value, like G value is there, HM value is there, but what about this VW2 and U2? These two values are not there. So we need to calculate, first one will calculate the U2. U2 is nothing but, this is tangential velocity at the exit, at the outlet condition. The formula is for this is pi dn by 60, pi dn by 60. So which d? That is outlet means outer diameter, so second diameter. So here we can put the value of pi into 1.2 and into, this is n is given 200 divided by 60. If you see this one, you can solve it here itself. This is 3 and this is 10. Again this will be 0.4. So 0.4 into 10, that is 4. 4 into pi, 3.14. 3 into 4, 12, and 1/4, that is 12.56. So here itself we got the value of U2. Okay. And second one, what we need to calculate? VW2. So VW2, if you see here the outlet condition, where is the VW2 part? This is the VW2. So by which relation we can able to calculate the VW2, that we need to identify. So if you see the outlet condition, and here let me consider, okay, if I consider the 10 phi angle, because this is the phi angle is there and the angle value is given in this question. So what I'll do, if I consider the 10 phi, so 10 phi at the outlet condition, we can write the formula. This is VF2 divided by, actually I need to write this base, but this base is not known to us. So what we can write in on behalf of this, we can write this is U2 minus VW2. So we can able to find out, because remaining value known to us. So here only unknown is VW2. So we can find out this value. So what I'll write here, I'll take this terminology in the left hand side. This one I'll take it to the denominator. So U2 minus VW2 equal to VF2 divided by, this is 10 phi. Okay, in the next line, let me write, I need only the value of VW2. So what I'll write, I'll keep the VW2 one side, other side I'll keep it like U2. So otherwise I'll do one thing, I'll write this value now. Okay, otherwise one more steps you need to write. So U2 value is already we have calculated, that is 12.56 minus VF2 is given 2.5 and divided by 10 phi. So 10, this is 26 degree. I hope it is correct. Yeah. Now we can find out this value VW2 is equal to, this is 12.56 minus 2.5 divided by 10, 26 degrees. So that we can calculate from here with the help of this calculator. Yeah, so this is 26 suppose, and the trigonometric value of this one is okay, this is 0.487, 0.487. So anyway, I'll do otherwise one more time, like this is 2.5 divided by bracket start, this is 26, trigonometric value 10, bracket close, the same thing came. So you'll get the value of 5.12. So here I will write 5.125. So VW2 is 12.56 minus 5.126, you can write, or 13 you can write here. Your 2 digits are there, so you can write like this. So your part will get, this is 7.43 meter per second. So this is your VW2. Now we can put this value in this equation, and we can find out the value of efficiency. Manometric efficiency is equal to, this is G 9.81 into HM value, this is HM value is 6, and divided by VW2 is 7.43 into this is which one, U2 is 12.56. If I just calculate it, I can get the value of manometric efficiency. So I'll write in this way, let's make it 0, then in the numerator 9.81 multiply 6, and this division, bracket start, this is 7.43 multiply 12.56, 12.56 bracket close, and 0.630. So 0.630, or else we can write this is 63%. Okay, so this is our manometric efficiency. Okay, so one answer we got here now. And the second one, while calculating the second part, as I told you that I'll tell you two methods are there to calculate this. One is directly this formula we can use. By using this formula, we can find out the value of n. Another one step also there, I'll tell you that one. So first let's find out by this help of this formula, like n equal to 120, efficiency is given 0.63. Let's write this, and VW2 is already calculated, so that value is 7.43, and D2 is given 1.2. So this one, and divided by, this is pi value is there, pi into, this is 1.2 square minus 0.6 square. So we need to calculate this value so that we can find out here. Let's solve it. Yeah, this is the value already there. So multiply 120 into 7.43 into 1.2, 674. So 674.828. Okay, and divided by this total value is there, like pi into 1.2 square minus 0.6 square. So I'll do one thing here itself, I'll try to divide, bracket start, this is 1.2 square minus 0.6 square, bracket close. So this is 624.84, and divided by pi 198.89. So here I'll get 198.89 something we'll get here. Okay, so this is the value. So near about 199 we got here. Now, as I told you that another method I'll tell you to find out. So actually we know that the minimum speed required to start the pump. Okay, in the last lecture also we have discussed. So the minimum speed, at least it should be like the value of manometric head u square by 2g, u2 square by 2g minus u1 square by 2g. It should be equal to hm. Actually, it should be greater than or equal to hm, but at least for minimum one we can write at least equal. Okay, So in this terminology, actually U1 and U2 both are there, that is tangential one, tangential velocity. So U1 actually we can write, U2 we can write, this is omega into R2, and omega 1 equal to, sorry, this is U2, EU1 equal to omega into R1. This is angular velocity we can write. Now we can write this is equation, then put this value in this equation. This is square also, sorry. Now if you put this value in this equation, and finally we'll get like you can take a common of omega square by 2g. Let's take it common. Then bracket what will be there? We have, this is R2 square minus R1 square. HM value is already known to us. So HM value is already given, that is 6. So if from here we can find out the value of omega. We can find out the value of omega here. Okay. Now after finding the value of omega here, then we can write that omega equal to actually 2 pi n by 60. 2 pi n by 60. So here what I can write, n equal to, I can write this is omega into 60 divided by 2 into pi. So by that also, by this method also, we can able to find out the value of m. Here actually, if you tell like the value, omega square by 2 into 9.81, and this is R2 actually, this is D1, D2 given, from that we can write R1, R2. So R2 is nothing but 0.6 will come, I think, yeah, 0.6 square minus 0.3 square equal to 6. So here I can keep this omega square one side, and remaining things we will take it to the other side. So omega square equal to 6 into 2 into, this is 9.81, correct, 9.81, yeah, 9.81, and this will be divided by like 0.36 minus 0.9. Let's try to find out here how much. This will be 0.6 into 2, 6 into 2 into 9.81, this much, divided by bracket start 0.36 minus 0.9. Okay, 0.36, 0.09, not 9. Okay, that's why I'm getting how it came minus value. Anyway, so this will get again we need to write 6 into 2 into 9.81 divided by bracket start 0.36 minus 0.09, bracket close. Now we can write 436. Now 436 we need to root over, that is 20.288. So here we got the value, if you see omega equal to, we got the value of 20.88, correct. Now I'll put this value here, then we can find out the value of n. So let me multiply this with respect to 60 and divided by, this is how much, 2 into pi. So divided bracket start 2 pi, divided by 2, pi only divided, this one not divided, so 199.39. so here if you see, we got the value of 199.39 rpm. So here how much we got, 198.9, that means 199 we got rpm. So mostly both value we are getting the same answer. So if you are able to remember this formula, that also you can use, or if you know this method also, you can use this method. So both can be used to solve this problem. I hope you understand this problem, how to solve this for this minimum speed required for the centrifugal pump. If you're having any kind of doubt and query regarding this, you can give a comment on the comment box. Thank you.